Hello everyone, I am Simrandeep Kaur from Indian Institute of Science. So here I am going to present our latest results on ABA trilayer graphene. So we have seen various odd denominator fractional quantum Hall states, and I will show you in the presentation that how we can control the particle hole symmetry of these fractional quantum Hall states in ABA trilayer graphene. So coming to the introduction part about the graphene systems, single layer graphene is formed of a single sheet of carbon atoms in which carbon atoms are arranged in a hexagon pattern. Looking at the band structure at low energies, which we probe it through transport measurements, so it has a linear band dispersion. Whereas if we add another sheet of carbon atom to this, the band structure completely changes, and in this case we will have a parabolic band instead of a linear band. So now if we add one more layer, which is trilayer graphene, so usually as we increase the number of layers, the possibility of getting different stacking sequences also increases. For example, in case of trilayer graphene, we have two possible stacking sequences. One is ABA trilayer graphene and other is ABC trilayer graphene, which we can get naturally through mechanical exfoliation. Now, just because only small shift in the stacking sequences, which it leads to the completely different band structure for these systems. For example, in case of ABA trilayer graphene, it is a multi-band system in which it is formed of monolayer-like band and bilayer-like band. Similarly, in case of ABC trilayer graphene, it is a single band system with a cubic dispersion. Apart from the different band structure, the one property which makes them more different from each other is the behavior under the application of the vertical displacement field. So this is the device schematic, and we have applied the interlayer potential to the outer layers to these layers. In case of ABA trilayer graphene, as we put the interlayer potential, the resistance at the charge neutrality point do not change much. But in case of ABC trilayer graphene, as you will see here, there is a huge increase in the resistance even if we put a small potential difference. Hence, there is a band gap opening in the ABC trilayer graphene, whereas in case of ABA trilayer graphene, there is no band gap opening. In my talk, I am going to focus on ABA trilayer graphene and going to discuss about the quantum Hall effect in this system, since there is a huge band modification and interesting things happens in this system. Now, since I'm going to talk about quantum Hall effect, I want to give a brief introduction about the quantum Hall effect. So this is a device schematic with a normal 4-probe measurement setup. Under the application of the magnetic field, in the classical regime, we have a transverse resistance which is having a linear relationship with the magnetic field, and we have a longitudinal resistance which is independent of the magnetic field. But in case of quantum regime, we start developing the plateaus and we have the oscillations in the longitudinal resistance. Now, when these plateaus come at the integer values, we call it as an integer quantum Hall effect. Now, to understand the origin of these plateaus, now let us consider the density of state picture for the metal, for the two-dimensional electron gas. So, under the application of magnetic field, we start developing the Landau levels. But this is a case for ideal system with no disorders. But we have disorders in the system, and this lead to a broadening of these Landau levels. So we have localized states here and the extended state at the center of the Landau level. And these are the localized states which lead to the origin of these plateaus. However, this is not the only case. When we increase the quality of the sample, we increase the magnetic field in the system, we start seeing the formation of plateaus even at the fraction values. As you will see in this, so this is the data by Stormer. So in this case, we see numerous plateaus developing at the fractional values as well. Now, to understand the origin of these plateaus, so let us understand, let us take the case for nu equal to 1 filling factor. So this is a schematic for two-dimensional electron gas with a magnetic field passing through it, and these orange circles are the electrons. In case of nu equal to 1 filling factor, all the degeneracy has been filled and there are no available states. So each electron is associated with a single flux quanta. Now, as we increase more magnetic field, we will have more flux quantas in the system. Now, electrons have the chance to minimize their Coulomb energy. So they do it so by attaching 3 flux quanta to 1 electron and staying away from each other. So this is the case of nu equal to 1/3 filling factor. In a simpler way, we want to understand it. So we have a one flux quanta and one particle, which we also call the composite fermion, and this will form a nu equal to 1/3 state. And in a composite fermion picture, if we call it as a single particle composite fermion and then one flux is attached to it, then this is the case of nu equal to 1 filling factor, and hence it is a nu of equal to 1 in the composite fermionic space. Now, the question is what is particle and whole part of fractional quantum Hall state? See, we do not see only a 1/3 state, we see numerous odd denominator fractional quantum Hall states. For example, this is the 1/3 state, which is n equal to 1 Landau level. And if we talk about the 2/3 state, that is n equal to -1 Landau level. If we talk about other fractions, this is n equal to 2 Landau level, and this is n equal to -2 Landau level. Similarly, this is n equal to 3 Landau level, and this is n equal to -3 Landau level. Now, if you see clearly, this part forms the particle part of the fractional quantum Hall state, and this part forms the whole part of the quantum Hall state. Now, there is a numerous theoretical discussions on the particle and whole symmetry in the fractional quantum Hall state. So what does that mean is that, so nu is the filling fraction where the fractional quantum Hall state occur. So if it is somehow related to 1 minus nu value and there is some kind of symmetry associated with these two filling fractions, then we call the system is particle whole symmetric. For example, what are the things which can be symmetric? Their energy gaps are similar, their effective masses are similar, the disorder broadenings are similar, and there is one other important factor which quantifies the amount of particle whole symmetry present in the system, that is the Landau level mixing factor. So that is a ratio of the Coulomb energy upon Landau level spacing. Now, in case of gallium arsenide, so it has a dependence on B, which means that as we increase the magnetic field, this Landau level mixing factor will be very small, and hence we will have a very nice particle hole symmetry in the system. But at low magnetic fields, we will not have nice particle hole symmetry in gallium arsenide systems. But in case of single layer graphene, it has no dependence on B, but rather it has a dependence on Fermi velocity and the dielectric constant of the system. Fermi velocity we cannot change since single layer graphene has a constant Fermi velocity. But the dielectric constant we can change by changing the substrate on which we are putting the single layer graphene. We can put it on SiO2 in vacuum or even in HBN substrate. This will completely change the Landau level mixing factor. For example, in vacuum, the Landau level mixing factor is 2.2, and in case of SiO2, it drastically reduces. It becomes 0.4 to 0.5, and that is why we can realize the particle hole symmetry in HBN substrates. So there is a recent paper by Chetan Nayak where he has studied the effect of Landau level mixing in single layer graphene. So this is the theoretical plot where this first plot shows the Laughlin wave function as a function of Landau level mixing factor, and this is the gap as a function of Landau level mixing factor. This is for n equal to 0 Landau level, the fractional states, which is 1/3, and this is for n equal to 1 Landau level state. Now, if you see the plot first, for n equal to 0 Landau level, the Laughlin wave function is quite stable against the Landau level mixing, like it is surviving till a value of 2. But in case of n equal to 1 Landau level, so the 2/3 are very sensitive to the increase in the Landau level mixing, whereas it still survives, but then again 1/3 also dies off with the increase in the kappa. So which means there is a breaking of particle hole symmetry as we increase the Landau level mixing factor in the system. However, the problem with graphene is that we have to change the substrates to realize this physics. But in trilayer graphene, as I have given the introduction, we can tune this Landau level spacing with the help of vertical displacement field. How we can do it, I'll show in the next slides. So this is the device schematics for the ABA trilayer graphene. So we have used dual graphite gate configuration. So this is the resistance versus number density plot. So this is the mobility of 4 lakh. And these are the fractional quantum Hall states which we have seen in order to understand the origin of these fractional quantum Hall state. Let us look at the band structure. So they mostly come from the 0th Landau level of monolayer like band, and all of them are odd denominator states. Now this is the temperature as a function of filling fraction plot for different fractions between 2 and 3. As you can see, this is 8/3, this is 7/3. So basically this is the particle part and this is the whole part of the fractional quantum Hall states. And if you see, they are very nicely symmetric about each other. Now, if we really want to quantify the symmetry, we have calculated the Arrhenius plots and calculated the activation gaps for different magnetic fields. And we see that, so this blue circles are for 7/3, and this blue open circles are for 8/3, and these triangles are for 12/5, and this green triangles are for 13/5. So this is the whole part of the fractional quantum Hall state, and this is the particle part, and they have a very similar thermal broadenings, very similar effective mass, so I have not put the values here. And the dependence with the magnetic field is also same for these 8/3 and 13/5 states. Now, what happens with the application of the displacement field? As I have told, like in trilayer graphene, we can tune the energy spacings, Landau level energy spacing with the displacement field. So this is the data for low electric field, which is 0.15 volt per nanometer. And as we increase the electric field to a bit high value, which is 0.5, so the whole part goes away, whereas particle part survives, which means whole part is very sensitive to the electric field as compared to particle part. To understand it more, so this is the, so we have quantified the dips, which is delta R, and then we have plotted it as a function of electric field. And what we see is that after a certain critical field of 0.2 volt per nanometer, the 7/3 still survive, but 8/3 die off quickly. Now this is the color plot where we can see the dying off of 11/3 and 8/3 states in this. Now to understand why the whole part is dying off but not the particle part, so we see how the trilayer graphene behaves when we apply the electric field. So these are the three layers. The center one is a mirror plane. So at zero electric field, the outer layers are identical to each other, so there is a mirror symmetry in the system. But when we apply the electric field, they both will have a different interlayer potential. It will break the mirror symmetry and it will cause a mixing of the two bands. So these are the two bands. One is the monolayer-like band and outer is the bilayer-like band. So as we increase the electric field, the mixing between the bands have started, and at sufficient high electric field, we will have a strong trigonal warping in the system, and which lead to complete mixing of the bands. And because of this mixing, we have a huge tunability of Landau level spacings as a function of electric field. So this is the delta, which is proportional to vertical displacement field, and this is these are the various Landau levels which are there in the trilayer graphene, and we are mostly focused on Nm equals to 0 Landau level, where we see the fractional quantum Hall states and where we see this breaking of fractional quantum Hall states. So in order to understand if these crossings are actually real or we can see it in experimental data, so this is the data at 2 Kelvin. So where we nicely see all the crossings, like this rectangle is nicely matching with this rectangle, and this hexagon is nicely matching with this hexagon diamond, and this is also matching with this this part. So basically these crossings are actually real and they are probed experimentally. And we have tried to calculate the kappa, which is the Landau level mixing factor between the monolayer-like and this bilayer-like, which is coming close to each other. And we see a huge enhancement of kappa after 0.2 volt per nanometer, and which lead to the breaking of the particle hole symmetry in the system. So to conclude the slides, so we have seen various odd denominator fractional quantum Hall states in the monolayer-like band of ABA trilayer graphene. So this is a plot. Then we have seen the presence of particle hole symmetry at low values of the electric fields. Then we have seen the enhancement of Landau level mixing factor between the 0th and the 2nd Landau level of bilayer-like band with the application of electric field. And then we, this Landau level enhancement in the Landau level mixing further lead to breaking of particle hole symmetry. And from this we can form a system. ABA trilayer graphene can form a single system where we can control the particle hole symmetry in different regimes for the fractional quantum Hall states and can study this physics. Thanks for that.
Okay, questions?
For ABC case?
So ABC right now there are not, fractional states are not seen in ABC trilayer graphene, but looking at the band structure and behavior with D, so that Landau level spacing do not change much in ABC because there is a band gap opening in that system and not the Landau level mixing is happening. So I think we should not see the particle hole symmetry breaking there.
Okay, thank you.
It's 2/3 one of the fractions that you saw.
Yes.
So that's supposed to have an electrically neutral mode that's just running around the boundary.
Yes.
So, you know, there were attempts to detect that in thermal transport.
Yes,
for
yes,
example,
yes.
like in the gallium arsenide and the new gallium arsenide systems.
Yes.
Is that
yes.
an experiment that you think would be interesting to do here?
Yeah, so we will now, since recently we have started seeing the fractions going to zero, so now we are trying for further this like 2/3, like what are, is it actually a counter propagating modes and all, so we are working on it right now.
Okay.
Yes.
Other questions? All right, if not, let's thank Simrandeep for a very nice talk.
Thanks.